Hello and welcome to the lecture The Large Language Model Part 2. In this lecture, we are basically discussing the LLM training algorithm. We first start with pre-training, followed by sampling, data usage and evaluation. And we conclude the lecture by discussing the fine-tuning procedure. Now, we can understand that the training algorithm of large language model basically consists of some procedure, and first of all the tokenization, then pre-training, then sampling, etc. Now what we have discussed tokenization in the last lecture. In this lecture we are going to discuss pre-training. Now here this transformer model are being pre-trained by virtue of this sentence. Now as we have understand that our large language model are pre-trained by a huge text corpus. Now take a small example, you can understand how actually this is being pre-trained. Now here you can see there is the input sequence of 10 tokens. One is this is the sentence, is starting with the start of sentence token. Then the sentence, actual sentence, the for every action there is equal and opposite reaction. Okay, and this will going to generate for every action there will be an opposite reaction. So it is the same sentence, but one thing you have to note that this sentence is start of this token SOS, that means start of sentence token. When this sentence is coming, this particular token is coming, this neural network is going to produce the TK1, that means token 1 that we intended for. You see that for is not been given, so SOS is given, so it will, if it is already trained, that the actual our intention is that. So what actually that means, that what we are, how we are going to train this neural network, that means the transformer, that for the given token they will give the next token, that the first token of the sentence. So this is the for is not seen by this particular. Next you can understand when we say the SOS and for, this with these two tokens this neural network is going to generate every. So one thing you have to understand is very clearly here, that this kind of model, that particular model is when we are, this first is being given, then this is the for is when we generated. When these two been given, SOS and for, then this is being given. When this is SOS for every, then this action is being generated, and so on. In this way actually it is being, so in this way it is being trained. Okay, now when it is being trained, then we generally, and how it is being trained, then when we get some output we calculate the cross entropy loss, and based on this loss or gradient of loss we run the backpropagation to update the model parameters. So this is the way actual this neural network, or basically this transformer model, is being trained. One thing I repeat, that it is the next, this particular thing is for the every tokens generate the next tokens. It's not the, it's not just copying, it is the next token, and that is this neural network is being trained. When it is being trained, then at the time of inference, that this what we are basically trying to do here or expect from the model, that this is the same thing. If the 3 tokens is being given, that is 1 1 3, then that you can see the 4th token, actually it's not 4th token, in the output sequence is the 3rd token, is this next token here, action will be generated. That is basically this pre-trained transformer. They already been trained. Now it will go into action. Now this action, when it is being generated, these things is append to the input, append to the last token to the input. When it is appended to the next thing, what? The next input sequence is this start of sentence for every action. Now this will be generated, and if it is put to your pre-trained transformer, so then it is being this for every action, that this there will become. So for every action, the next token is being generated. So this transformer is trained such a way that at the inference time we expect that this transformer is going to generate the next token, and that is this next token is coming to the input sequence, appended to the input sequence to get this sentence. What is the next? So exactly here there is coming as append in there, and we can get this. So in this way we get the actual sentence back. Only difference is that it start with start of sentence, now it is the end of sentence. A sentence is bound becomes same. So every time we get the next token. Okay, so that is the basic training and the inference of this large language model. The next module of the training algorithm of large language model is sampling. The sampling in LLM refers to the method that used to select the next tokens from the probability distribution predicted by the model. Now I am going to see this slide that has been in the very first lectures. Then in LLM there is some process or modules. First tokenization, then tokens are fed to the language model, and this language model basically samples, basically produce some probability distribution. Just for example, there is an after what will be the word that may be dual with that probability, equal with this probability, every with this probability, action with this. Now from this probability distribution, sampling is what is doing, that choose what to. In general, as a very simple strict case, we get the most probable word, that equal here. So sampling is a procedure that choice or that basically select the next token from the probability distributions. That probability distribution means this probability distribution from the tokens that produced by the language model. And then after that it tokenized to produce the actual token or actual word. So this is the sampling. Now instead of always choosing the highest probability, are we always going to take the highest probability? May not be. Sampling introduces some randomness so that the generated text can be more diverse and creative. Always the highest probability they not choose. Okay, and we go by this. We'll seal it. Now what we have seen, that steps engine generation, input prompt to the model. So that is the input prompt. This is the prompt to then it is tokenized and fed to the model. Then model predicts a probability distribution over tokens. Now it generates probability distribution over tokens. This is the probability distribution. Then the sampling choose a particular probability distribution or particular tokens out of this probability distribution. Okay, so that sample a token based on the probabilities. So and then this token is add to the input sequence and repeat until the end of generation. So that is the normal procedure. Now if we take an example of what is, so if there is a prompt artificial intelligence is, so it may be the case that these are the next few tokens, the transforming many industries. Again, another thing is the key domain of the science. That is also kind of. So the idea is basically here that it is not always give the same tokens. So each word is chosen through repeated sampling. Sampling allows the model to occasionally pick other plausible options as above example, making the text generation less repetitive. If it is always take the same as highest probability or something, then this model is basically very much repetitive kind of. But here you can see that artificial intelligence is the key domain of data science. That is different than transforming. So this sampling procedure is something like that, by which we can just roam about between this very much repetitiveness and the randomness. Okay. Now there is a different types of sampling techniques, and these are common sampling techniques. Greedy decoding. That means just always see always select the highest probability token. It is deterministic, simple, but very much repetitive, less creative. It's very easy to understand. Then random sampling. We choose the token randomly. There is a definitely it is some more creative, but may not be always very useful or very correct. Now another thing is called temperature sampling. Temperature is what? Temperature is basically a control parameter that controls the randomness. That this pi, this is basically E of log eta by t, and this is summation of j. So if temperature is kind of low, then it's a safe answer. So safe answer means it's more deterministic. And if high temperature is high, there is a creative answer. But when this is low temperature, it is deterministic but repetitive in this end. If it is a high temperature, then it is some sort of randomness is being imposed so that the answer will be more creative, but not that much deterministic. So another kind of sampling is a top K sampling. Top K sampling only keep the K most probable tokens of all the tokens. Other tokens are discarded, then sampling happens only among this. Maybe some use the sampling procedure become computationally expensive. Another important top P sampling, that is called nucleus sampling, that select the smallest set of tokens whose cumulative probability greater than P. That P is equal to 0.9. So those tokens have been taken. If you add the probabilities, that will be greater than P. Method is widely used in modern LLMs. So these are the common sampling methods. Okay. Now next thing, what is very important, that is the data. That how data is, we can say, we have already said that this large language model has trained on a huge text corpus. That the data is one of the most important aspect of pretending this large language model. Okay, now let's see. Now generally we use the internet crawling for this. So common crawl snapshot of the entire web produced by the non-profit Common Crawl with billions of pages of colossal clean called corpus. So this is 2020 paper in C4. 156 billion tokens use of English, filtered what's in it, mostly patent, text document, Wikipedia and news sites. So these are the kind of data set that have been created by internet crawling, and you can see the size 156 billions of tokens. Now given a data set, this data sometimes call is not that much you can say that clear data. So there is some problems with data. So some filtering technique is required with respect to the quality of the data and safety of the data. Now what is the quality? Quality is subjective. Both are subjective, quality and safety. Many LLMs attempt to match Wikipedia, books, particular websites. The genuinity of the data. And need to remove the sensitive text. Some text is not that much good for the social things or some things. So that's why we can exclude this. Deduplication at many levels. So URLs, documents, even lines. So this is the quality measurement that has been made on the data. In the same way, we have to ensure the safety. That is also subjective. Toxicity detection is important, although that has mixed result. So that is one important thing. And it can mistakenly flag the data written in the dialects like African American English. So there is some sort of this kind of language problem. So there is some sort of measure with respect to the quality and safety has been taken to filter out the raw data, so that it will be more useful or more suitable for this training or pre-training purpose of the large language models. Okay. Now here you can say this is taken from this pile step, that is the training corpus. Say basically the PubMed Central, these are the data, the source of data, arXiv, and then PileCC, then Open Web Text 2, Stack Exchange, Wikipedia, and so on. These are the different kind of GitHub code. These kind of things are being taken. Okay, so the huge data set on this composition of the pile by category is a pre-training corpus. Okay, we used to pre-train many of the famous large language models. So these are the academic. This blue is academic purpose. This green is from internet. This is prose. This is for dialogue. This yellow. This gray is for miscellaneous data. So this is the source of data. Now another thing, what amount of data? That is also an issue. The amount of data used for LLM pre-training is extremely large, that we have said, because the model needs to learn the language patterns, facts, reasoning patterns, and word knowledge from the text. So it is not only the next token to predict, rather when side by side it learns the language patterns, facts, reasoning patterns, word knowledge from this textual data. So modern large language models typically trained on billions or trillions of tokens. So it is generally, this data is usually measured by tokens, not words. And these tokens is, one token is 4 characters somewhat, and one token is 0.75 words in English. 1 billion tokens means 750 million words. For example, GPT OpenAI by OpenAI 175 billion parameters trained on 300 billion tokens. And the data set mostly, the data source mostly include books, Wikipedia website, code repositories, etc. Llama 2 by Meta is 2 trillion tokens. Understand how big the data set for training data set. PaLM by Google is 540 billion parameters and trained on most 780 billion tokens. Also, this amount of data being used for this training purpose or pre-training purpose. So why so much data is required? Large data set helps to model to learn the grammar and syntax, factual knowledge, that what are the facts, reasoning patterns, multilingual abilities, domain knowledge, science, coding, etc. And definitely more data generally improves it. So it is not that is important to understand. It is not only next token to predict, as a side by side it's a grammar and syntax, factual knowledge, reasoning patterns, multilingual abilities, and so on. So that's why this so much data is required. So what we have seen, that a huge number of data is required. Now, but there is some problems with scrapping from them. What are the problems? First is copyright. Much of the text in this data set is copyrighted. So not clear if the fair use of the doctrine in US allows for this use. This remains an open legal question. Some nations will basically have some reservation to use. They have to take in the consent for using it. Website owners can indicate they don't want their site overcrawled. So that is also another problem. Privacy. Website can contain the private IP address and phone numbers. So these are the issues of crawling just the data to get. So these issues we have to. Okay. So what we have seen that data is one of them. And the last part of this training algorithm is evaluation. So in evaluation, what we are going to see that is called perplexity. So perplexity is a common metric used to evaluate how well a language model predicts the text. So there is kind of perfection. That in simple terms, it measures how surprised the model by the actual sequence of words. So intuitively, perplexity, how many choices the model is confused between an average. So this is the been statistically is being defined in this, that is the product of P of xi being 1 and this is to the power I, where P of xi is the predicted probability of the token xi. And perplexity is in general between 1 and total size of the vocabulary. If it is a 1, perfect prediction. If it is a less than, basically less than 10, model choosing between 10 possible tokens. And if it is 100 or something very close to the size of the vocabulary, very uncertain. So perplexity simply is e to the power cross entropy. Okay. So minimizing cross entropy loss during training automatically reduces the perplexity. So that make the model more robust, more accurate. Okay. So the final point of this large language model is fine-tuning. So fine-tuning is one of the very major module for this. Now we start this discussion with a question. What happens if we need our LLM to work well on a domain it didn't see in the pre-training? Let's say we have a model is basically pre-trained on some data or textual data, basically from English language. But now this pre-trained model on English is required to perform on a medical data that has not been trained with medical data. In this case, what we have to, generally it's not that perform that much good because it has not seen. So here comes the fine-tuning process. So fine-tuning an LLM is the process of taking a pre-trained language model and training it further on a smaller task-specific dataset so that it performs better on a particular task or domain. As we said in our set, data is normal English language. It's been trained on normal English language corpus and it has been taken to the medical domain. So what we have to do, then we have to have a data set that may not be that much good, that much big. It's a small data set, but it's this pretend large language model and train it further on this smaller task specific data. Task specific is a medical data, medical text. So it may be smaller, much smaller than, because pre-training is done on a huge data set, but it is not that much high data set, but task specific data set, medical text for medical, so that it performs better this on a particular task. That is called fine tuning. So large unlabeled text corpus, that is basically used to pre-train this large language model. It's called pre-training. And what is fine tuning? A smaller task specific data set is been given to this pre-trained large language model. It is already been pre-trained, please, so that it is fine tuned for this domain, for this large language model, so that it can perform better on a particular task or domain that is this data is related to. That is the basic idea of fine tuning. So pre-trained LLMs learns the general language knowledge, that at the time of pre-training, this knowledge is very general, but they may not perform optimally for a specific task. Okay, so just for example, you can say the medical domain, legal domain. So fine tuning helps the models to be specialized in specific domain and follow task specific instruction and improve performance with level data. Okay, so this data may be supervised data, this smaller data, because it's small data. So for example, a general LLM might not perform well in medical diagnostic test, but after fine tuning on medical data, it can perform much better. That is very essential of fine tuning. So that you can say that what is the fine tuning steps? Start with a pre-trained LLM. So it is a pre-trained LLM, and continue this, prepare a task specific data set. This data set we prepare and continue training the model with this data set. Update model parameters slightly so that the is more accurate, and evaluate the performance and to see how much improvement is being done. So this is the basic fine tuning process. So there is a different type of fine tuning. First of all, the supervised fine tuning, that use the level input output pairs. So this data, that is a small data set that has been used as a this task specific data set. This is level data, because level data is costly, but it's a small data set. Another is instruction fine tuning. Model learns to follow the instruction. For example, that if you say this translate to French, input is hello, output is bonjour. So this is the way, this is the kind of instruction is being given. Another is reinforcement learning fine tuning. There human feedback is used to improve responses. So this is different type of fine tuning. Another is parameter efficient fine tuning. Instead of updating all model parameters, only small additional layers are fine tuned. That is very common technique. You frequently see this technique, that not all the parameters, because this number of parameters in LLM is very high. So just last few layers we update, and this is the different types of fine tuning. So in this lecture, what we have understood, that we basically continuing the pre-training thing or LLM training. Okay? We start with pre-training, then sampling procedure, then how data are being used or what amount of data is being used. Then we see the evaluation of this LLM methods or LLM tools, and then the fine tuning use to make it more accurate in a particular specific domain. Okay. Next lecture, we start encoder only transformers. Thank you very much.